Yes. Okay, it started. Okay. Yeah. So can you go back to that unit cell? Actually.
Just in case if you want like to post it, I don't mind posting. You post it, but can I close the camera?
No, no, no. Please, 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 please. Yeah.
Yeah, can I?
Yeah. 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 Please, please. Yeah.
Okay, and then you can share. Then you can share
Yeah.
the
Yeah. Can you show me that one? Yeah. I will tell you. Yeah. Okay. So the thing is like, see, uh, let me annotate and then plot it for you. Okay. Can you open that paint for me? I can show you. Can you
again.
open the paint for me? Paint.
Oh, paint. Okay.
Okay. So see the thing is, okay. So the thing is like, for example, you have, see, you have a unit cell. Okay. Then you have a source here. Okay. For example, source is your excitation port basically. Okay. So here you are just, like illuminating the plane waves like this. Okay. Then hit on this surface, then it gets reflected basically, because in the
Yep.
unit cell you have, for example, a substrate, and then this one is metal, this is substrate, then you have a uh, yeah, patch or whatever structure you have.
Yep.
Okay. Okay, 1 minute please, let me go to uh, a room so that you will be hearing properly.
Okay. Take your time. It's fine.
Yeah. Yeah. So you have a unit cell, right? So what it does is, so you have a source here. So source here, right? Source here. So it just, eliminating the plane waves. Okay. Then it hits on this one. It induces the current basically. Okay. Current on
Mhm.
this surface. So Ampere law, right? Whenever the current
Yep.
is induced, so current will produce the magnetic field. Magnetic will produce current. So either way is possible, right? And
Yep.
you have two metal plates, one these two in between dielectric substrate. So this can act as a kind of capacitor, or we
Hmm.
can say defected capacitor. So it can create a two metal having, you can create a electric field basically, right?
Hmm.
This
Right.
electric and magnetic field, the electromagnetic things happens. Okay. So when it hits, then it will just come to, see, there is a edge diffraction will happen, then it will just impinge on this, then it is a ground plane, or we can say reflector, it just reflect back. Okay. So
Hmm.
the moment it enters in this one, this is the boundary basically, then
Hmm.
it will get impinge, get inside, somehow. Okay. And then comes back. So it will create a delay basically. Okay. A delay,
Okay.
right? Delay, we can call it as a phase delay. You
Hmm.
can, other words called as, phase. So how I am saying delay as a phase. So for example, you can see that, this is sine wave, right? It's just a sine wave. Okay.
Yep.
So this we call it as 1t, right? 1t, or you can call it as 360-degree, right? One sine wave is, equivalent to 360-degree, one cycle basically. Or we can call it as a time versus amplitude, you can plot, or if so this 360-degree. So what will happen is, see, with this waves will be propagating like this, and again comes back. So it will get a delay, right? For example, let's say here you are having, this is the starting point, you are just, get inside and comes back. But for example, by the time you are reaching this time basically, so which means, you are having delay of, for example, 360-degree phase shift you are experiencing, right? Your
Yeah.
wave is, but that is hold good for the, free space basically. But here what we are having, it is not a free space, it is just, dielectric, which is
Yeah.
having, 2.1 or whatever it may be. So it will
Hmm.
have a further delay, because why? Because see, you have a lambda g, right? Lambda g,
Yeah.
guided wavelength, which is lambda naught divided by square root of epsilon r.
Epsilon R.
Epsilon r or epsilon naught epsilon r. So epsilon r, sorry, epsilon naught
Yeah.
is this
Epsilon R.
one, right? So what will happen is, whenever the dielectric constant changes, your guided wavelength will be changing, right? Okay.
Hmm.
So accordingly, the phase also gets changed, basically. That's how
Hmm.
you will experience the phase. Okay. So
Hmm.
now So in S1 plot, you have a two amplitudes. One is, sorry, I can see like this. This is magnitude. The other one is phase, like this. Okay, just So if you see, this resonance, you will see zero crossing, zero phase crossing in the phase plot. Basically, this is the amplitude. Okay, so what is S11? S11 is nothing but reflected voltage divided by incident voltage, right? Incident
There
voltage.
is always should be always sorry, Professor, for interruption.
Yeah.
Always should be zero crossing between the reflection and the phase, right?
No, I will
Always.
explain it. I will explain you. Okay.
Okay.
So we reflected divided by V incident, right? That is how we define basically.
Okay.
So reflected means what? So whatever is getting reflected. Incident means what? This is what incidents. So
Incident.
ideally, ideal reflector, what to happen? Whatever you impinge, it just reflect, right? So
Mm-hmm.
100% reflection. If it is 100% reflection, what you will get here? You will get one, right?
Mm-hmm.
Reflected voltage is same as that of the incident voltage, right?
100%.
So 100%, so which is 1. Okay, so if you take the logarithmic of this, then what you will get? 0 dB, correct?
Zero.
Yes,
Yeah.
that's what you are seeing. Okay, so the 0 dB is here. Okay, then you are getting resonance. Okay, because of these inherent resonant characteristics of this particular patch, you are getting a resonance. So where you are getting for example, some drift in the reflection, so which is around, for example, 0.25 dB, which means what? 0.25 dB, let's say, or let's say I will tell you in numerical terms. So let's say reflected voltage is 0.9. You are supplying 1 volt, but reflected voltage 0.9. So how much is the percentage of loss? 10% is the loss, because
Yeah.
90% is reflected, 10% is loss. Okay, that's what we are quantifying in terms of dB, if you want to.
Mm-hmm.
Okay,
Mm-hmm.
and this phase, right? So whenever you are seeing the resonance, okay, the resonance is kind of a zero crossing. Basically, zero crossing means what? Where you will see resonance is what? Where you will see the the reactance effect is nullified, right? When reactants are not there, so what will happen? You will see the resistance alone, right? So
Mm-hmm.
resistance means it is zero phase. So resistance does not have any phase, right? Reactants have, for example, capacitance or inductance have a phase, but resistance does not have any phase.
No, no
That's
face.
why
Yes.
you are having, and the resonance you are having zero, right? Zero phase.
Okay.
That's how
Okay.
this definition will flow. And if you see here, that's why you can see here. Can you remember, can you correlate whatever I explained to you, right? So this is the resonance basically. If you plot, for example,
Yeah.
you can just,
There is a phase. There is another the one below. It
oh,
is
okay,
the
okay,
phase. Yeah,
okay.
the phase. Yeah.
This is the angle. You can just see.
Just yeah.
Yeah, you can
No.
see here. You can see
Yeah.
here. See, just a
From
two
minus
point.
90 to 90.
Can you see here? Zero
Yeah.
degree. The same thing.
Okay.
Yeah, that's it. You
So
can just. Yeah.
zero at exactly should come at 2.26.
Yes, exactly coming, right?
Okay.
So that's how it
Okay.
comes,
Okay.
because it is just
And
resonance,
this is the
right?
maximum. Okay. 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 I got
Yeah.
it.
So that's how
Perfect.
this plot is. Yeah. Any other
And
doubts?
and
Yeah.
and the phase we take it from minus 90 to 90. This is I know, but why? Can you explain to me why we consider it from only from minus 90 to 90 as a bandwidth?
See, the thing is like, see, it has a some background basically. Can we?
Yeah, you want me to do a new one? Okay, perfect.
Okay. So see, the thing is like, for example, you are, having an array. Okay. Okay. Array.
Hmm. Hmm.
You are placing unit cells like this, right?
Hmm.
Like this. Okay. So now what will happen is, see, you are expected to give this unit cell to give, offer, for example, 90-degree phase shift, or 180-degree phase shift, let's say. Okay.
Okay,
So I can have, for example, I can it may not be exactly 180 degree. It is never possible. Okay. It is not ideal case, right? It can
okay,
be, 145 or 135. Okay. Or it can be 215 or 225. Why? Because see, this calculation, this unit cell is simulated for one frequency, mid frequency, right? You might be
Okay.
considering the one frequency, right? But the moment you change the frequency, what will happen? Wavelength changes. Wavelength change means what? Guidal wavelength changes. Guidal wavelength changes means, again, it translates to phase, basically phase change.
Mhm.
So that's how, the thing is, the moment you move out of the frequency, the design frequency per se. So what will happen is there is a offset, right? For example, you can say for example, it cannot be 180-degree, it will be minus 147 to 215, like that it will be
Mhm.
there. Okay, so this range, right? So now why they are calling it as minus 90 to 19, to 190, sorry, plus 90, right? So what will
Yeah.
happen is, see, they might have analyzed, see, it is from the research that if you keep, if you vary from minus 90 to 1, which context you are talking about, minus 90 to plus 90? It's for
Like
AMC or what?
phase.
AMC
Phase.
or
Yeah,
uh,
yeah, AMC, artificial magnetic conductor.
magnetic conductor. Okay.
Yeah.
So the thing is, like, if you are, varying from minus 90 to plus 90, you will not see significant change in the performance of that particular AMC, basically, on the whole.
Yeah.
Okay. So that's
Okay.
why they point, in general, they have, minus 45 to plus 45 and minus 90 to plus 90. And so that's how, say, it's like a compromise, right? So minus 90 to
Okay.
plus 90, you will get a reasonable, performance, right? That is why, they chosen this as a bandwidth, basically. So see, which means, see, so whatever frequency accommodates, for example, let's say, one frequency is like this, another frequency is like this, another frequency is like this. Okay. For example,
Hmm.
whatever frequency, the difference between these two curves, or the plus 90 to minus 90. For example, let's say this is minus 90, this is plus 90. So within this, whatever frequency, this is the, let's say this is F1, F0, let's say, design frequency, this is F2, this is F1. Okay, so this is the frequency range. Bandwidth will be F2 minus F1.
Hmm.
So the phase difference between, let's say, see, what you can do is you can just plot, for example, this is, I think, a unit cell size or frequency, whatever it may be. So whichever is giving, you can just, for, let's say, you are plotting the phase versus frequency. Okay, so you are having like this. Okay, like this. So you take a minus 90 and plus 90. Well, the corresponding frequency range is your bandwidth, basically. That's it. Okay,
Hmm.
so why they are considering this minus 90 to plus 90 and bandwidth? See, if you want to operate, see, you cannot operate any system with the, for example, 100% same performance as that of the throughout the bandwidth, right? 100%. Maybe, for example, if it is a very, very, very good design, then you can get, for example, 99%, for example, let's say you are expecting a gain of, for example, 21 dBi gain.
Hmm.
Okay, so you may get, for example, 20.9 if it is a very, very good design, so means extreme design, I would say. So 20.9 throughout the frequency, but whatever band you are considering. So as in such a way that, and sometime what happens is you are making compromise. Okay, you can say I can have a 0.5 dB difference, it's fine. I can have 1
Hmm.
dB difference, yeah, it's fine. I can have a 3 dB difference, it's fine. So that is a compromise you are making, right? So that's how these numbers are, arrived at, basically. Okay.
Okay.
Yeah.
Okay. Thank you so much. Thank you. I mean, it was a struggle and as well understanding them somehow.
Yeah.
I went, okay, two more things. I have
Yeah.
one thing. Okay, let me just show you this unit cell I'm working on and like straight to the point. So this I'll close, right?
Yeah. Yeah.
I'll open another one. So you saw the unit cell, and then I made another, sorry, another one with 1.57 thickness and at 5 gigahertz. Ah,
Okay.
I'm just trying. I
Okay.
mean,
Okay.
I'm just trying. There's nothing like,
Okay.
but I got like, for example, for this one, something like this. it looks like completely nothing.
Nothing. Yes, 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 yes. Yeah, I think
Yeah.
yeah.
Yeah. So I want now to draw on this one something
Okay,
that will resonate at, for example, let's say 6 giga or 5 giga.
okay,
And to know these dimensions, I have to go and to use, so I mean, to shorten the time and the efforts, the
okay.
best way is to go and to use some algorithms or artificial networks, neural networks,
Yes.
or transfer functions.
To tune that
And then,
yeah, dimension and to get the desired performance. That's what you are trying, right?
yes. For example, if later on I want to do beam steering, or I want to do a reflector with 0 degree phase,
Okay.
0 phase, sorry, I can get that one as well. But for now, what I'm trying to do, just to understand these artificial algorithms, how can I implement it and get the best design, for example, for beam steering?
Oh, okay, okay, okay.
And another angle, for example, after 30 degrees, another beam will come from another, but we mount it at the top of the patch antenna or array patch antenna. So
Okay.
our so it will scatter in different the refractive way in different directions. This is
Okay.
another idea, but in general, just to draw the thing on this unit cell and to try to get from a program back, reverse method. Like
Okay.
they call it even reverse modeling, reverse modeling.
Okay.
Yeah, this is what I'm trying to do. And one tiny thing before
So
before
reverse modeling, you meant to say you want this radiation pattern, this much steering, for which you have to optimize your design, right? Correct?
yeah, yeah,
Okay.
yeah,
Okay.
yeah. And one more thing, because do you remember when I showed you the cubes, the unit cell, but that got mistaken, like there's some errors in it.
Yeah, yeah, yeah.
The distance between each cell and cell, is that calculated, or is there any kind of formula, or you just plug them in a similar manner, like, or similar distances from each other?
Which one you are telling about? This one?
I'm talking about this. Do you remember the? Okay, let me just wait.
This distance, right?
No, not this cell, not this cell.
Okay.
Okay, wait. I'll show you. I'll show
Okay.
you. I'm talking about, yeah. I'm talking about this one. Yeah, this one. But like the ground, and we had too many of them.
Okay.
So the distance when you want to distribute these unit cells, the distance between each unit cell and the other one, the gap between the two unit cells, is that
That is,
calculated?
lambda by 2. Usually we keep lambda by 2. See, that has a reason behind that. For example, um, you know, uh,
Why is that working?
uh, okay. The thing is like, see, the thing is like, so that, what we call, um,
Like here, you see here, when you said, wait, let me just change the color. This is one unit cell. Yeah, okay. The dimensions of one unit cell is lambda over 4, but distance from this unit cell, the other unit cell, from here to here.
see, the thing is, see, if you, 1 minute, let me tell you one thing. Like,
Yeah.
oh, what is that? Like, for example, unit cell size you have, right, during the simulation, correct?
Okay.
That is the interelement spacing between them. So how it works is, see, you have this unit cell, for example, let's say lambda by 2, okay, lambda over 2.
Okay.
So in principle, you have, unit cell like this. unit cell like this. Center to center is your lambda over 2.
Lambda
Lambda,
over 2.
yes, yes.
Okay.
But,
But I
but,
did the
but,
cell.
no, no,
Sorry.
but, if you have a same unit cell size, it will just, touch, right? If you have a same unit cell
Right.
size, yeah.
Right. Right.
That case, I think, we have to see, the thing is, see, this one is for the, for example, see, this spacing, no, you have to optimize to get the, for example, desired beam forming very easily. So this has a limitation. For example, if you have a beyond lambda by 2 or whatever it may be, what will happen is, you cannot steer the beam beyond certain extent, basically. That's why,
Okay.
they compromise. For example, you want to steer the beam like this, no, like this, like this, like this, and this angle, no, there is one radar equation available. So where, this the optimizing this uh, uh, optimizing this unit cell different the gap between the unit cell. So what will happen is, so it will control the, it will limit the beam direction, basically. So which direction, like, for example, otherwise we can say beam sweeping range, which means -30 to +30 or -20 to +20, sometime -10 to +10. So it is purely depending upon the unit cell characteristics and this one. So what is the, in principle, what is the logic behind this? For example, you have unit cell like this, you have unit cell like this, like this. So you have multiple unit cell, right? It has to
Mhm.
constructively form a beam, right? Constructively form a beam. If you are exciting with appropriate weights to steer the beam like this, so what will happen is, if you have a huge gap between the unit cell, what will happen is, each will, some unit cell will become an independent radiator, basically. Okay. So what will happen
Okay.
is, it will have a side lobes, basically, grating lobes also
Wow.
sometimes. So some array, part of the array contributed for this beam, some array, part of the array contributed for this beam. So grating lobes will come. So in order to suppress that, we apply several algorithms. So it is like, two things. One is, you have to optimize the spacing between the elements. Another one is like optimizing the weights in such a way that you should not get this grating lobes or side lobes. You will only get the beams like this. That's it. Okay. And also, see, it is after all, dipole, right? Maybe we can say monopole. So it will have some kind of back lobes, right? So the moment you steer the beams like this, these back lobes will shoot up here. Okay. So that's
Okay.
why we have to optimize these things. So IT ultimately what we are doing is constructively, constructive interference, means constructive interference, or we can say this all, will be coherent and then form this beam. And at the same time, you should not have any other beams. So in order to do that, we have to optimize the spacing between the elements and the weights. The element characteristics also will matters a lot, because the thing is,
Okay.
see, you have a unit cell, you are simulating with the, just, for example, let's say, we call it as,
Locate port. Well, yeah.
no, forget about this, we call it as, I think, I forgot the exact name. So we can see, see, like, for example, on the broad side, we can say this is the unit cell. Just, you are, exciting with the broad side. Sometime if you excite this case, what will happen to this face? For example, whatever face you are getting, right, whatever face you are getting, it will vary. When you change the incident angle, it will vary, because it is
True.
seeing a different architecture, right? For example,
Mhm.
let's say this is the unit cell, this is the unit cell. Okay. The moment you impinge here, it is seeing these patches completely. The moment you impinge here, it is seeing something else, right? The dimension is
Mhm.
different and everything is different. So that's
Mhm.
how, there are multiple factors to consider during unit cell design as well as the array design. Okay.
Okay. Okay.
So
Um,
any other point
sorry.
to discuss?
Yeah, just when you were talking, there was a very important point I wanted to point out.
Yeah.
Um, yeah. Just imagine we put the array metasurface at the ground,
Okay.
and at the on top there's a patch.
Okay.
Okay, how do you feed the ground in this case?
So why do we need to feed the ground? Because there is a
So
one.
we don't need to feed the ground, right?
No, 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 no. See, there are two way to feed the unit cells, any patch or any antenna, basically. One is direct feed, which is normal microstrip patch or whatever it may be. The other one is spatial feed. Okay, spatial feed is what what you are exciting with the flock input basically. Okay, flock
Okay.
input or whatever you are emulating that. So spatially, you are keeping the feed, and then you are eliminating to the elements basically. Okay.
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 Okay. Yeah, yeah. Okay. Thank you so much. Because I was thinking like, okay, I said like, okay, you don't need to, because it is only a resonance, a resonator that will receive the current, will turn into unexpected magnetic behavior. So
Correct.
you don't need power to, but
Yes.
just to make sure.
Yes. Yes. Yes.
Okay.
Yes. Yes.
Okay. Okay.
So I think I have to go to other meeting.
I finished. I finished.
Yeah.
I'm really thankful to you, Professor.
Okay.